Okay, we're looking at Lesson 8, Day 1. Again, putting some old topics together. New. So today we are going to be using area of a circle. And there is only one formula for the area of the circle, unlike circumference, where we had the two formulas. Here, we only use the radius, and it's the radius squared. So, like in the example, or in this first problem, when we're given the diameter, if they write something next to the center, the assumption is that's the value of the diameter. We need to divide that by 2 to get the radius, and then we square it. Put the pi on the end and our unit squared, and we have the exact area. If we want an approximation, we could use 3.14, or we could use the pi key on the calculator. Like with the circumference, all three of these will be different. Again, this is the exact, and the second approximation using the pi key on the calculator will always be a larger number because it has more significant digits. If we look at the second example here, they are giving us the radius, so it's a little bit more straightforward. We just substitute the radius into the formula. We square that 6 to get 36 pi centimeters squared. We can approximate pi with 3.14 or the pi key on the calculator. We look over here, we're given the radius, so we just square the radius, put a pi on the end, inches squared. Using 3.14 as our approximation for pi, we get 452.16 meters squared, and using the pi key again, we get a little bit more, 452.39 meters squared. Some review of last week. The measure of an arc is equal to the measure of its central angle. The measure of an arc is measured in the same units as an angle, degrees. The length of the arc is not measured in degrees. The arc length is calculated using the arc measure and the circumference of the circle. The length of an arc is a portion of the circle's circumference. Okay, our second warm-up is very similar to one we did last week. Last week we were highlighting the exterior, the circumference of the circle. Today we're going to go ahead and shade in the actual sector. And we're just going to take one of these sectors of our equal partitions. So here they ask for 3 equivalent sectors, so we make that little peace sign like we did last week. We're going to shade in just one of the 3. And we know ultimately the fraction that it reduces to is 1/3. But if we take the measure of the central angle, 120 over 360, we can see numerically where that 1/3 comes from. Here we can say visually where the 1/3 is. 4 equivalent sectors, we get 360 divided by 4, which would be 90. This is 1/4 of the circle. We've got the 5 equivalent sectors. I know that will be 1/5 of the entire circle. And if I make the ratio of the central angle to all degrees in the circle, I could see I will get that 1/5. 6 equivalent sectors, so I'll start with 3 and divide each one of those in half. Shade one of them. So this will be 1 out of 6, or 60 out of 360. I need 8. Again, you're using a straight edge. I'm just freehanding it. I'm going to take my 4 and I'm going to cut each one of those 4 in half to get 8. I'll shade 1 out of 8. This is 45 out of 360. Here they gave us the 10 and shaded it for us, so we could just go 1/10. And that would be 36 degrees out of the total of 360. And they were nice enough to give us the partitioned circle here into 12 equivalent sectors. So we shaded 1 out of those 12. That central angle is worth 30 out of the 360. One additional warm-up here today. I want to revisit our special right triangles. We have a 45, 45, 90, right triangle. We know x and y are equivalent. Or I'm sorry, this and y are equivalent. So I just fill that in. And I get this by multiplying my side by the square root of 2. So I end up with 6. 45, 45, 90. These two are equivalent. I'm reversing it this time, so I'm going to divide 4 by the square root of 2 to get 2 square root 2. Again, 45, 45, 90. So b and 2 square root 2 are identical. And I'm going to take this and multiply it by the square root of 2 to end up with 4. Our second type of special right triangle is a 30, 60, 90 right triangle. But also has a special relationship between the sides. This one was when we wanted to get shorty. We remember that from a long time ago. So I find the shortest side, everything keys off of that. The hypotenuse is twice the short side, and that side across from the 60-degree angle is shorty times the square root of 3. So here I do not have shorty, but I always want to find that first. So I have the hypotenuse. I'm going to reverse it and divide by 2. So shorty is 8, and then this one is 8 square root 3. Again, not given shorty. That's this one here, but we want to get shorty first. We are given the side opposite the 60 degrees, so to get shorty, I'm going to divide by the square root of 3 to get 5, and then double that up to get the length of the hypotenuse, which would be 10. 30, 60, 90, we have shorty. This is an easy one. Double up shorty to get the hypotenuse. Multiply shorty by the square root of 3 to get that longer leg. All right, now finally for our lesson, that was a lot of warm-ups. A dartboard is a good example of concentric circles. Concentric circles are circles that share the same center. Draw and name 2 examples of concentric circles and share those examples with a classmate. So just kind of think about things that you see that are circular, one circle nested inside the other, but that they share a common center. All right, we're looking at this colorful dartboard here, and we want to identify how many concentric circles we have. We're going to let this black point be our center, and so I highlighted each circle that I found, and I have 1, 2, 3, 4, 5, 6 concentric circles. And here they want us to find the area of this dartboard. They said the diameter is 180 millimeters. And again, for the area, we need the radius. So I think I would take this 180 and divide it by 2 to get 90. And so the exact area of the dartboard would be 90 squared, 8,100 pi, and our units are millimeters squared. Now we're just going to look at one sector of the circle. So this is like what we did dividing, examining the dartboard. The dartboard has 20 sectors that they've called out. And the central angle of each sector would be 360 divided by 20, or 18 degrees. And so the ratio of the intercepted arc of one sector to the circumference, so to the whole entire circle, is 18 out of 360, or 1/20th, because we have 20 pieces and we're just looking at one of them. The ratio of the area of one sector to the entire circle has to be the same ratio here, 1 to 20, or the fraction 1/20. And so now we're going to use that information to go ahead and calculate the area of one sector. So So we have 1/20 of the entire area that we just calculated. So we have 8,100 divided by 20 is 405 pi millimeters squared. And you could check that, multiplying the 405 by 20 to get back to the 8,100. All right, what we just did is we used the formula without even knowing on how to calculate the area of a sector of a circle. So it's very similar to our formula we used for arc length. So let's kind of go back and visit that here. The length of an arc, you recall they represented that with S, is the arc measure, so that would be in degrees, over 360 times the circumference, which was 2 radii times pi, or a diameter times pi. If we look at this formula, the area of our sector is our measure, again, of the central angle over 360 times not the circumference formula, but the area formula. So this is a fraction of the circumference, this is a fraction of the area. We kind of compare these. Both formulas use a fraction created by the central angle measure over 360. However, the arc length formula uses the circumference of the circle, while the sector area formula uses the area of the circle. So one is fraction of the circumference, the other one is the fraction of the total area. Just taking a look at the example here, they give us that the shaded sector's angle is 45 degrees and the radius is 4 centimeters. We always want to update our drawing with the information given. Then we're going to get our formula. We have 45 out of 360 times r squared pi. The exact area is 2 pi centimeters squared. AO is 6 centimeters. They tell me this is 60. Now they want the shaded area. So I think to get this angle measure of the shaded area, I need to take the total degrees minus the unshaded part to get 300. So we subtract 360 from 360 to get 300, and then we use this angle, 300 out of 360, r squared pi. Do some math. The exact answer is 30 pi meters squared. So go ahead and try these two on your own. And when you're ready, we'll go on to the next page and we'll talk about one more topic, the segment of a circle. A segment of a circle is the region bounded by a chord and the included arc. So it's this part right here, kind of the crust of our pizza. And we're going to figure this one out too. So we're going to start with a slice of pizza. We're going to use a straight edge and put in that chord AB. And then we're going to highlight the two distinct areas that we just formed. So we've got the crust out here. And then we've got the rest of the piece of pizza over here. Pretty bad shading. You're doing a neater job than I am. So if we look, I see now we have a composite shape. Rather than looking at just the sector of the circle, I can see this segment piece and a triangle. piece right here. So I can think of this total area as an area of the two composite shapes. So the area of the sector would be the area of the triangle plus this new thing, the area of the segment. And then what we can do is solve this formula for the area of the segment to get the area of the segment is the area of the sector minus the area of the triangle. And this is how we're going to calculate sector area. So we've got our circle's radius is 8 centimeters. This is 90 degrees. We need to determine the area of the shaded segment. So this part right here. We're going to do it twice. We're going to get the exact answer and then an approximation using 3.14. So we start out with our area of the entire sector. 90 over 360, 8 squared pi, and that's going to simplify to 16 pi centimeters squared. Now we need to calculate the area of the triangle, our other part of our composite shape here. 1/2 base times height. So half of 64 or 32 centimeters squared. So the exact area of our segment is 16 pi minus 32 centimeters squared. We want to approximate the area. We need to take our 16 times our pi, or times our 3.14 as our approximation for pi. So I have 50.24 minus 32, which is 18.24 centimeters squared. Okay, so before we go on and do a couple more of those, we want to just make sure we understand the different components we're looking at. So let's identify whether we have a sector of a circle, a segment of the circle, or an arc of the circle. I look here, this is clearly a sector. It's inside a piece of pizza. So you want to think of like a piece of pizza. The whole thing. That's a sector. Here I just have the part on the outside, so I am talking about an arc of this circle. I look here, I don't have the whole piece of pizza. Here I have little pieces of the crust, so this is a segment of the circle. And again, I have just the crust again, so this would be a segment. Okay, and then the last little piece here, we're going to be given the area of the segment and asked to solve for the radius. And so we just set it equal to the formula there. We have our segment area would be the area of the sector minus the area of the circle. And then we do some algebra, solving for r, taking the square root. We know it's really the absolute value of r when we take its square root of r squared, but a negative value does not make sense in this application, so we just have this entire value here to get the value of r. If you have the TI-84, you can just plug that in all at once to get your answer. You would get your square root and your fraction, and we're going to type in 9 pi's minus 18 all over fraction of a pi over 4, or 1/4 of a pi, minus a half, or 2/4. And we get the radius is 6 centimeters. And I'll tell you, there is a shortcut to do these problems. I like doing them the long way, and I suggest that you do that also. But if you think you have a better way of calculating it, or maybe a shortcut, if you want to come up and talk to me and we can discuss that to make sure that you are on the right track.